Welcome to this presentation by Harvey H. Harper, focusing on the significance of concentrations in determining the performance of best management practices. Throughout this session, presented for BMPFast in January 2026, we will delve into how concentration levels play a crucial role in pollutant removal and why field testing under expected concentration conditions is absolutely necessary for accurate assessment. In this module, we'll be exploring the critical conditions that govern the removal effectiveness of any best management practice, or BMP. A key factor we'll focus on is the influent concentration entering the BMP, as this fundamentally determines how much pollutant can be removed. We'll also discuss that every BMP has a minimum achievable concentration. There's a limit to how clean it can make the water. Our understanding of typical BMP performance is largely derived from field-collected data, which provides real-world insights into their effectiveness. This is why it's so important that field data be collected and analyzed thoroughly before any BMP is put into general use or receives permitting. We'll consider the journey from the raw input to the final discharge, understanding how these principles apply. Here we're looking at typical phosphorus concentrations found in Florida residential runoff. This slide presents field-collected data comparing the concentrations of phosphorus in runoff from two common stormwater management systems, the traditional curb and gutter system versus the use of vegetated swales. Across 10 different sites, the data consistently show that concentrations of all phosphorus species are lower when runoff flows through a swale system compared to a curb and gutter system. This finding is significant because it demonstrates that swales provide effective pretreatment of runoff, actively reducing phosphorus levels before the water enters other drainage systems or natural bodies. It really highlights the value of swales in managing and improving water quality by removing phosphorus. Here, we're looking at some field-collected data comparing typical nitrogen concentrations found in residential runoff in Florida. Specifically, we're examining the differences between runoff collected from traditional curb and gutter systems versus more natural swale systems. The graph illustrates the concentrations of dissolved organic nitrogen, particulate nitrogen, and total nitrogen across both types of systems, based on data from 10 different sites. What's clearly evident from these results is that concentrations of all nitrogen species, whether dissolved organic, particulate, or total nitrogen, are consistently lower in runoff collected from swale systems compared to what we find in curb and gutter systems. This provides significant justification for the value of swales in effectively reducing nitrogen loads in stormwater runoff. Here, we're examining field-collected data from wet detention pond discharges, specifically in watersheds where reuse irrigation is practiced. What we're observing is a direct impact from the use of reclaimed sewage or reuse water within these catchments. Our findings indicate that phosphorus concentrations for most parameters in the pond discharge are consistently higher than what you would typically find in raw residential runoff. This elevation in phosphorus levels means that to meet post-treatment standards, a significantly larger runoff treatment volume will be required. Ultimately, these results suggest that the current practices involving reuse irrigation may not be compatible with the new stormwater rule, posing a significant challenge for water resource management. Understanding the typical distribution of phosphorus species in residential runoff is crucial for effective treatment. We find that approximately 70% of the phosphorus present consists of what we consider removable species, primarily soluble reactive phosphorus, or SERP, and particulate phosphorus. The remaining fraction includes dissolved organic phosphorus, which is more challenging to remove and typically requires biological processes that occur at a slower rate. When we consider the performance of wet detention ponds, if we achieve an 85% removal rate for these easily removable species, our overall total phosphorus, or TP, removal becomes about 60%. This calculation, 70% multiplied by 0.85, gives us that 60% figure. This 60% removal is quite representative of the maximum TP removal typically achieved in wet ponds with standard detention times, which are often designed for annual residence times greater than 21 days. It's important to note that for much longer detention, times, perhaps around 180 days, a greater portion of that more recalcitrant dissolved organic phosphorus may also be removed, leading to potentially higher overall removal efficiencies. Let's look at the typical distribution of nitrogen species found in residential runoff and consider their fate within wet detention ponds. Based on field-collected data, a significant fraction, about 48% of the total nitrogen, consists of what we categorize as removable species. These typically include ammonia, nitrogen oxides, and particulate nitrogen. Dissolved organic nitrogen, another major component, is generally removed through biological processes, but at a much slower rate. If we consider a high efficiency for the removable species, say 85% removal of that 48% fraction, we can estimate an overall total nitrogen removal of approximately 41%. This figure is quite consistent with the maximum total nitrogen removal rates observed in many wet pond systems. Even at long detention times, which might stretch to over a year, only a portion of the dissolved organic nitrogen may be removed. It's important to understand that even with extremely long detention times, the total nitrogen removal in wet ponds generally cannot exceed a range of 40 to 50%. However, it is usually greater than 40% at the typical design annual residence times of over 21 days. This data allows us to estimate the potential for nitrogen removal in these systems. The wet detention pond is essentially a man-made lake designed specifically for pollutant removal. These systems rely on processes that occur within a permanent pool of water. They are subject to all the natural physical, biological, and chemical processes found in surface waters, which contributes to their highly predictable performance in removing pollutants. Looking at the diagram, you can see key design features that facilitate these processes. The permanent pool is crucial, as it's where much of the treatment happens. Within this pool, we observe three main types of pollutant removal. Physical processes are primary, with gravity settling being the most significant. Here, heavier particles simply settle out of the water column. The efficiency of this process is heavily dependent on factors like the pond's geometry, its overall volume, the residence time of the water within the pond, and the size of the particles themselves. Adsorption onto solid surfaces also plays a role in physical removal, and its efficiency is also a function of residence time. Biological processes contribute as well. This includes the uptake of nutrients and other pollutants by algae and various aquatic plants, as well as the metabolism of pollutants by microorganisms present in the water. Finally, chemical processes, such as co-precipitation by metal oxides, further aid in pollutant removal. The diagram illustrates other important design elements, such as the normal water level, or NWL, and the top of bank, TOB. You'll also note the littoral zone, typically designed with gentle slopes like 6:1 or 4:1, which is a shallow area crucial for supporting aquatic vegetation that contributes to biological treatment. Features like the weir and orifice control the outflow, and the water's control elevation, managing the water level and residence time within the pond. This diagram, as you can see, comes from the applicant's handbook and helps us understand these important design considerations for these effective systems. This slide illustrates a comparison of nitrogen concentrations between raw residential runoff and the discharge from wet detention ponds. What we consistently observe is a significant reduction in the concentrations of all nitrogen species after the water passes through a wet pond. This reduction is particularly evident for inorganic nitrogen, encompassing both ammonia and nitrate, and is primarily attributed to biological assimilation processes occurring within the pond. These measurements are crucial as they document the effectiveness of wet detention ponds and represent the typical range of concentrations found in stormwater. Let's look at a comparison of phosphorus levels between residential runoff and the discharge from wet detention ponds. The data shows that most of the ponds included in this analysis had relatively long detention times, often exceeding 100 days. This extended time within the pond contributes to a consistent finding. The concentrations of all phosphorus species are significantly reduced once the water is discharged from these wet ponds. These measurements effectively document the performance of wet detention ponds in treating phosphorus, demonstrating their ability to lower these pollutant levels within the typical range of concentrations found in stormwater. Field measurements have consistently shown that the discharge from wet detention ponds contains extremely low concentrations of inorganic nitrogen. Specifically, both ammonia and nitrite, or NOx, are typically found at concentrations very close to their limit of uptake by the pond's ecosystem. At this point, dissolved organic nitrogen often becomes the largest remaining nitrogen species in the water. Similarly, soluble reactive phosphorus, or SERP, is also present in extremely low concentrations, again nearing the limit of what the system can effectively remove. Total suspended solids are also quite low. What this means is that these nutrient concentrations are so low that the pond's treatment capacity for any significant additional removal is essentially exhausted. We refer to these as irreducible concentrations. For total nitrogen, we typically see levels around 400 micrograms per liter, and for total phosphorus, concentrations range between 10 to 15 micrograms per liter. Nutrient removal in wet ponds is primarily a function of detention time. When we talk about detention time, we're referring to the average annual residence time, which is essentially how long the water stays in the pond. From extensive field concentration data, curves have been developed that illustrate the removal of both total nitrogen and total phosphorus as a direct function of this residence time. These relationships help us understand how ponds remove both particulates and dissolved species. However, it's crucial to understand a few key limitations. These relationships were specifically developed for untreated runoff only. They do not apply if the runoff has received any form of pre-treatment before entering the pond. Regarding the removal of dissolved pollutants, this process is fundamentally a function of the concentration present in the water. We observe that removal rates tend to decrease as the water column concentration decreases. Ultimately, removal stops when an irreducible concentration is reached, a baseline level below which further removal becomes impractical. For total nitrogen, this irreducible concentration is approximately 350 micrograms per liter, and for total phosphorus, it's about 10 micrograms per liter. To enhance the nutrient removal capabilities of wet detention systems, floating wetlands, also known as floating islands, can be effectively employed. This process involves growing plants directly on specialized mats, which are then strategically deployed and maneuvered to selected locations within the water body. Over time, these plants develop a substantial root mass beneath the mat, which is key for nutrient assimilation. Our research indicates that this enhancement method proves particularly valuable in settings with elevated water column nutrient concentrations, often a consequence of reuse irrigation. For example, we observed an approximate 10% reduction in total phosphorus concentrations. However, it's also worth noting that we saw about a 12% increase in total nitrogen during the study period. Consequently, this approach is best suited for applications where nutrient levels are already high or in watersheds impacted by reuse irrigation. It's crucial to recognize a key limitation. Once available inorganic nutrient concentrations fall below certain minimum thresholds, the additional nutrient uptake by the plants becomes negligible. Our findings suggest these minimums are around 10 micrograms per liter for soluble reactive phosphorus and approximately 130 micrograms per liter for total inorganic nitrogen, which are often typical concentrations found in many standard wet ponds. When we examine product removal claims, such as a 90% reduction, it's crucial to understand the conditions under which these studies were conducted. Many product testing studies are actually performed using concentrations much higher than what we typically observe in real-world runoff. This means that product efficiency claims are often based on the most favorable testing results, which may not accurately reflect how the product performs in actual conditions. For example, products or technologies designed for wastewater, which deals with very high nutrient streams, may not be effective when applied to runoff, where concentrations are generally an order of magnitude lower. While a product might achieve a 90% reduction in soluble reactive phosphorus during testing at high concentrations, its actual removal when applied to natural runoff with its much lower concentrations, could be near zero. Therefore, when you are evaluating a new product, it is absolutely essential to always ask for specific information about the influent concentrations that were used in their testing, to ensure they are reasonable reproductions of actual field conditions. Adsorption media represent a key approach for removing stormwater pollutants. This process works in two main ways. Pollutants are adsorbed or adhere onto the solid surfaces of the media, and particulate matter is physically entrapped within the media's structure. For these systems to operate optimally, particularly for biological processes, they must have proper environmental conditions, such as low dissolved oxygen. When these specific conditions are met, we refer to them as biosorption activated media, or BAM, as these environments enhance the removal capabilities. These media are carefully developed to maximize the removal of specific target pollutants. The compositions vary widely, but evaluated media often include mixes of common materials like sand and clay, various carbon sources such as compost, sawdust, cardboard, paper, or agricultural residues, and sometimes other specially manufactured media tailored for particular uses. It is critical that any adsorption media system demonstrates its effectiveness through rigorous testing in the field to ensure it achieves the desired pollutant removal. Continuing our discussion on adsorption media, it's crucial to understand that all sorption processes are fundamentally concentration-based. This means that sorption rates will increase as the concentrations of the constituents you're trying to remove also increase. Conversely, at very low concentrations, the rate of sorption will decrease until it eventually stops entirely. Every type of media has a minimum uptake concentration, meaning there's a certain point below which it can no longer effectively remove a contaminant. This minimum uptake concentration varies significantly depending on both the specific media type and the particular constituent being removed. A common challenge we face is that manufacturers' efficiency claims often lack comprehensive information regarding the full range of concentrations that their media can effectively treat. For practical application, there are 7 media that have been approved for use based on their proven field concentration reductions. While these are common, other media can be added under user-defined options within specialized software, such as BMPFast. However, when defining your own media, it is absolutely essential to clearly identify the concentrations and the mix of species involved. Always ask for field-tested data to ensure the influent concentration used in testing is truly representative of your actual field conditions. Shallow hardwood wetlands are characterized by their shallow water bodies, which overlay soils that are typically rich in nutrients, acidic, and often anoxic, meaning they lack dissolved oxygen. The water quality of any discharge from these wetlands is primarily determined by an equilibrium established between these unique soils and the water column itself. This process operates as a first-order reaction rate, meaning it's dependent on the concentration of substances present. An important characteristic is that this equilibrium is usually reached quite rapidly, typically within 3 to 4 days. What this means in practice is that if you have high concentrations of certain substances entering the wetland, they will be reduced as the system moves towards equilibrium. Conversely, if concentrations are initially very low, the system might actually release substances, leading to an increase in their concentration until that equilibrium point is achieved. Here, we're looking at nutrient equilibrium specifically within hardwood wetlands. What this means is that the nutrient inputs coming into these wetland systems eventually reach a stable state, or equilibrium, with the existing nutrient concentrations in the wetland soils. This phenomenon of equilibrium has been consistently noted with concentrations observed across various best management practices and field site locations. For instance, in these balanced systems, we typically see total phosphorus concentrations around 0.100 milligrams per liter, or 100 parts per billion. For total nitrogen, the equilibrium concentrations are generally in the range of 1 to 2 milligrams per liter, which translates to about 1,000 parts per billion. These figures represent the steady-state conditions where nutrient uptake and release are in balance within these wetland environments. In hardwood wetlands, we often observe a state of nutrient equilibrium, where the incoming nutrient inputs balance out with the amounts absorbed or processed by the wetland soils. This balance is crucial for the overall health and function of these ecosystems. For instance, studies have shown that total phosphorus, or TP, typically reaches an equilibrium concentration of around 0.100 milligrams per liter, which is equivalent to 100 parts per billion. Similarly, total nitrogen, or TN, usually stabilizes within a range of 1 to 2 milligrams per liter in these environments. These values give us a clear indication of the typical nutrient levels once equilibrium has been established. Wetland polishing refers to the final stages of water treatment, where wetlands are used to further reduce pollutant concentrations, particularly nutrients, to very low levels. A key component in this process is wet detention. Wet detention systems are designed to remove both solids and dissolved nutrients from water. However, their long-term efficiency can be somewhat limited because there's generally little direct uptake of nutrients by the vegetation within these systems. Over time, the water can also reach an equilibrium with the surrounding soils, reducing the soil's capacity to absorb additional nutrients. This can lead to a substantial reduction in the overall efficiency of a wet detention pond under certain conditions. To achieve even cleaner water, especially for sensitive environments, a hardwood wetland can be employed as a subsequent polishing step. Let's look at how nutrient levels might be reduced through this process. Imagine we start with influent water that has relatively high concentrations, perhaps 250 micrograms per liter of total phosphorus, and 1,500 micrograms per liter of total nitrogen. After passing through initial treatment stages, including potentially a wet detention system, we might see these concentrations decrease. For example, total phosphorus could be brought down to around 100 micrograms per liter, and total nitrogen might fall within a range of 1,000 to 2,000 micrograms per liter. Then, the water flows into a hardwood wetland, which acts as the ultimate polishing stage. Through the complex biological and chemical interactions within this type of wetland, nutrient levels are further significantly reduced. We can achieve very low concentrations, such as 35 micrograms per liter for total phosphorus, and approximately 750 micrograms per liter for total nitrogen. This demonstrates the powerful role of these advanced wetland systems in achieving stringent water quality targets. Let's now examine the nutrient equilibrium specifically within herbaceous wetlands. These are characterized by shallow water bodies densely packed with herbaceous vegetation. This dense vegetation provides a significant amount of physical structure, which in turn supports a large and diverse population of algae, bacteria, and other microorganisms. These organisms often form a dense gelatinous layer directly on the plant stalks, commonly referred to as zooglole. The water in these wetlands meanders slowly around these plant stalks. This slow, winding movement provides an extensive opportunity for various uptake processes to occur, where nutrients are absorbed by the vegetation and the microbial community. Interestingly, while the soils in these wetlands are typically anoxic, meaning they lack oxygen, they have relatively little direct contact with the overlying water. This limited interaction helps ensure that sediment release of total phosphorus remains minimal. Overall, the unique structure and dynamics of these shallow herbaceous wetlands contribute to a specific nutrient balance, an important characteristic we've observed in similar wetlands that have been monitored. Here we're looking at a treatment train, which combines multiple treatment approaches in sequence to achieve greater contaminant removal than a single system alone. Our example here begins with a wet detention pond. This pond is highly effective at removing both solids and dissolved nutrients from the incoming water. A significant part of this removal is attributed to the uptake by the vegetation within the pond and the biology that attaches to the plant stalks. The efficiency of this initial wet detention pond is typically calculated using established removal curves. You can see the impact of this first stage by looking at the nutrient levels. Water entering the wet detention pond has a total phosphorus concentration of 250 micrograms per liter and total nitrogen at 1,500 micrograms per liter. After passing through the wet detention pond, the total phosphorus is reduced to 35 micrograms per liter, and total nitrogen drops to 750 micrograms per liter. Following the wet detention pond, the treated effluent then flows into a shallow herbaceous wetland. This wetland acts as a polishing step, designed to remove additional nutrients that were not captured in the first stage. This sequential design means that the combined efficiency of the wet detention pond and the herbaceous wetland is significantly increased compared to what a standalone wet detention pond could achieve. After the water has moved through both the wet detention pond and the shallow herbaceous wetland, the total phosphorus is further reduced to just 15 micrograms per liter, and total nitrogen is brought down to 400 micrograms per liter, demonstrating the powerful cumulative effect of this treatment train. To summarize what we've learned, the concentration of pollutants is a profoundly important consideration when both selecting a best management practice and evaluating its potential performance. Many removal processes operate based on first-order rate kinetics, which means the rate at which pollutants are removed will directly increase or decrease as their concentrations increase or decrease. It's also critical to remember that biological, physical, and chemical processes often require a certain minimum concentration of pollutants to even initiate effectively. Therefore, you must always consider the likely concentrations of your target pollutants in the source water when making a BMP selection. A key takeaway here is to exercise caution regarding manufacturer marketing claims. The removal efficiencies presented in literature or by manufacturers are frequently based on elevated nutrient concentrations, which is often where removals are greatest. Always make sure to ask about product performance specifically at typical stormwater concentrations, as these can differ significantly from the conditions used in laboratory testing. Let's continue our summary of key takeaways from this module. We've seen that relying solely on product removal efficiencies can be misleading. Manufacturers can often inflate these numbers by simply increasing the initial concentration during testing. Therefore, for a best management practice, or BMP, to have a truly accepted removal efficiency, it's crucial that the concentration ranges used during its testing are clearly stated. What's far more important than just a percentage of removal is understanding the minimum achievable concentrations for a given BMP. This tells us what the lowest pollutant level we can realistically reach with that particular treatment is. It's also vital to recognize that techniques successful in wastewater treatment aren't always transferable to stormwater. Wastewater nutrient concentrations, for instance, are typically about 10 times greater than what we find in stormwater. This significant difference means that a process effective in a high-concentration environment may not perform similarly in a low-concentration stormwater setting. This brings us to the importance of field testing. Before implementing any retrofit BMPs, especially, conducting thorough testing under actual field conditions is absolutely essential to truly understand its performance and effectiveness for the specific stormwater challenge you're addressing. Hopefully, through these discussions, you've gained a greater appreciation for the critical role of accurate concentration measurements in evaluating the real effectiveness of stormwater management practices. This presentation on the significance of concentrations on BMP performance was presented by Harvey H. Harper. With the completion of these learning modules, you can now proceed to Self-Test 1 and consider earning your certificate. Thank you for your time and attention.